here are the answers from the worksheet yesterday that you had. So what you will want to make sure you do is that you pause the video on this page so that you have a chance to look at those. This will also be in the daily planner. So as you are looking at those, so pause it if you need. In lesson 3 today, we are going to be looking at the rates of change that we are looking at. So as you look at lesson 3, one of the things that we're going to look at is, can we define the interval and rate of change? Think of rate of change, remember? Slope. Slope is our rate of change. So when you're going to go back to our rate of change, you know how to do that. You're finding your slope. That's our rate of change, m equals. Representing either the function notation, so remember function notation is when we talked about the f of x. How does it look like in a graph, a table, and then as we are looking at specific inputting an interval, we're going to compare our rates of change to 2 or more functions as we look at this. And if you look in your textbook, this is 9-2, the concept bytes, so as you're looking at where is this in your textbook. And then I can identify and interpret the meaning of the average rate of change using units in the real world problem. So thinking about rate of change, in this case, if we're looking at the points, these 2 points, how do we find that rate of change? This is telling us that it is a change in people per year. So where we have our year here, and we are talking about our population as our y-axis, okay? Now, as we are doing the problems, one of the first things that you are going to be asked to do is look at this equation, h of t equals 20t minus 5t squared, and it represents the approximate height of a ball that is thrown upward at a velocity of 20 meters per second, thus the 20t, and the height in meters that the ball after t seconds. So if we replace it with 0, the height is 0. If we replace 1, so someone said, how are you getting the height? H equals, you're using this equation. So 20 times 1 minus 5 and then 1 squared. So you're just replacing this equation. So if we are looking at that, we should have 15. Next, you're going to replace the parenthesis with a 2. So 20 times 2 minus 5 times 4. And you should get 20. I would like you to plug the 3 and the 4 in to see what you get for your slope or for your height of the ball. And what you should be noticing is that the ball went up and now it's starting to come down. So 0, 15, 20. Again, pause it. You should plug in 3 next. If you plug in 3 in the parenthesis for t, time, and get your height h, you should have 15, and the last one should be at 0. So it says we want to analyze our data in this tablet. What is our average rate of change? From 0 to 1. Remember, average rate of change is the change in y divided by the change in x. You can do this by subtracting your y coordinates over subtracting your x coordinates. And if we look at this, 15 minus 0 for subtracting our y coordinates, and remember, this is like our y, this is our x. If we're subtracting y's, 15 minus 0 over 1, so our rate of change is 15, and in this case, if we wanted to put it as 15 over 1, or 15, and we're talking about meters per second. From 1 to 2, what is my change? Well, I can take 20 minus 15, that gives me 5 over 1, so I have 5 meters per second. What is my change from 15 to 20? Well, going from 20 to 15, I'm going down. It's going to be a negative 5. This is still a change in 1. So negative 5 over 1, or simply just a negative 5. And the last one from 15 to 0 is going to be a negative 15 for my rate of change. And the question says, to analyze our data, what can this tell you about the graph? What does it look like? Well, first thing it should be telling us, it is definitely not linear, right? It does not have just the one variable, it has to the second power, and this is called a parabola. If we look at that graph, what is it going to look like? And I just want you to kind of do a rough sketch, and you're going to see this picture, and I'll have you pause the video so that you can kind of make this rough sketch. And really the key thing that I would say when I look at your rough sketch of this is that you put your y-axis on your paper, going down, and you put your x-axis, and then you probably have 0, and we know that we had after 15, so we want to see 15 and 20, and we have 1, 2, 3, and 4, and we just are kind of estimating. So at 1, at this case, it was at 15, and then 20, and then 15, negative 15, or 15, and then 0. So making those points to graph it. Pause it if you need to. And the question then that we take a look at is a toy car in this case, now looking again at rates of change. What is the distance the car travels in 1 second? So in 1 second we are at about, if we are looking at that number, we might say between 4 and 8, and it looks like a little less than 6, so we would say probably 5, and in this case we are talking about 5 centimeters. In 3 seconds, what are we looking at? And again at 3, I might say that I'm talking at about 13 centimeters. Where are we at 5 seconds? And at 5 seconds, excuse me, we are talking about, excuse me, 17 centimeters. It says, what's the average rate of change from 1 to 3? So if we are going from 1 at this point to 3 at this point, what is our rate of change? And if we are looking at that, change in y divided by our change in x. Our change in x from 3 to 1, 3 minus 1, is going to be 2. What is our change in y? Well, we had 13 minus 5. So 13 minus 5 gives us 8. 8 over 2 gives us a rate of change of 4 centimeters per second. But that's just from 1 to 3 seconds. What is it from 3 to 5? So again, change in y divided by change in x. How is my x value changing in seconds? 5 minus 3. At 5 seconds, how high was it? 5 seconds, it was 17. Minus 3 seconds, it was 13. Here I'm going to have 4 divided by, if we are looking at this, 2, which means I have 2 centimeters per second. And the question that we are looking at is, does the average rate of change increase or decrease? And in this case, it is decreasing. How do you know? Well, it went from 4 to 2. 2 is a smaller number. And if you look at the graph, here it was a bigger change to here it being a smaller change. So how does this show up on the graph? We might say that when we look at the graph that the curve is flatter as time increases. So the graph, if we are looking at that, the curve is flatter as time increases. But this only goes to a certain point, up to 6 seconds. And now it looks like it's at its maximum point. So as we are taking a look, it says, well, what do we remember about rates of change when we look at our linear function? Remember, that rate of change, what is that also known as? That is our slope. So when we are talking about slope, that is when we talk about a linear rate of change. That linear rate of change, it is always a constant number. Remember, when you do linear, you're always adding the same number, so it's either a constant addition or subtraction that you are doing. As we are looking at that, always to add or subtract is our pattern. Whereas when we are looking at exponential functions, now I don't know if you remember our exponential, but those are our growth factors, okay? So remember when we had the growth factor or the growth and decay problems? And what did our equations look like? So growth and decay were our two different kinds that we looked at. And remember, linear was the y equals mx plus b. Growth was y equaled something to the x power, usually. Growth was 2 in this case or not. And remember, that's when we have an exponential function. So kind of tying everything together for the year, exponential function. And our pattern that we were using, whereas in linear, our pattern was to add or subtract. In here, we are looking when it's exponential that we are multiplying. And we usually think of multiplying even if we're multiplying by a fraction. So what you're asked on the top of the next page is to take a look at these different equations and look at your rates of change. So from 0 to 1, 1 to 2, 2 to 3, what is our rate of change? And complete each one. So what I would like you to do right now is you're going to pause the video. When the video is paused, you will fill these in. I will be writing these in, but I want you to pause the video, and then when you start it back up, you will see those answers. You can now see these different rates of change as you're looking at them. Here, nothing changes, always the same. Here, what's happening each time if we look at those rates of change? Well, from 3 to 6, 9 to 15, 15 to 21, we are always adding, in this case, 6. Always adding 6. So those are continuing to go up. This, if we are looking at that, is going to be our quadratic. And the exponential, what's happening from 2 to 6, from 6 to 18, we are multiplying by 3. So as we look at those, we now want to think about, in this next situation, your last page of notes. And here it says we want to look at these different types of functions, and it says answer the questions based on the data on the 3 tables as you look at your notes up above. It says, what do you notice about the average rate of change in the linear function? So in that rate of change from the first table in that first graph, we should have noticed that that rate of change is constant. It is always the same number. And when we talk about it being the same number, we're actually talking about them. All of those rates of change were actually 3 when we were looking at those. Somehow it seems that my pen has died here, so I'm not exactly sure. All right, we'll try and continue. So constant, or it's that same number. Notice it was always a 3 in our case. What do you notice about the quadratic, the second one? If we are looking at that the rate of change increases, so our rate of change is actually increasing. And as I'm writing these, what I'm thinking is I'm going to have you pause the video after they're written down, and that rate of change is increasing by, in this case, the same amount. Each time it goes up by 6. But if we are looking at that, this is a pattern for, if we are looking at our table, pattern for an arithmetic sequence. So all the things from earlier this year, they're all kind of coming back as we finish the end of this, because you have a common difference. If we are thinking about that, that common difference in our slopes is the 6. What do we notice about the rate of change in our exponential? As we are looking at that one, our average rate of change is a ratio. Our rate of change is a ratio. What is the ratio in this case? Our ratio is that we are multiplying by 3 each time. So this is going to be for a geometric series. Remember geometric, when we are doing those, geometric is when we are going to multiply by the same thing. Okay? And then it says, the last one says to compare the rates of change from the quadratic, the exponential, and the rate of change increases more quickly. And as we are looking at this one, I'm just going to kind of move this aside so you can see it, and you can pause the video while I read it. The average rate of change for an exponential function increases more quickly. This is why a graph, when we are taking a look at that graph, this is why the graph is steeper and than the curve for a quadratic function. So kind of as you look back at those tables and graphs in your notes, and as you're writing down this last part, you might need to pause this to see that. Your worksheet, you are asked to find the axis of symmetry, the vertex for each one as we are looking at those. So you're looking at the axis of symmetry and the vertex. The height of the ball as you are looking at these, so still looking at some of the same problems. And then this is our last page, and this is really the new stuff. 16, 17, and 18 is kind of what this lesson was talking about with those rates of change and finding the rates. As you finish this and as you are working, we will again be taking tomorrow probably a homework quiz that'll be on the lesson I2. So tomorrow you will take that in class, and hope all goes well.